Hello guys, my name is Divyaprakash and I'm a data scientist with over 1.5 years of experience. In this particular channel, we have took up a challenge where I have promised to do data science for each and every day and document my progress on whatever the things that I'm doing. So as part of this, we were working on an ship performance analysis dataset to forecast the performance of the ship over time. So we first took up the dataset, did some kind of EDA to understand what the dataset is of. We visualized the missing values, and since it is a maritime dataset, we first investigated whether it is of a single voyage or is it of multiple voyages, and we kind of visualized that as well. So right now, what we'll do is since we have concluded that the voyage, it is not a single voyage and it contains data of multiple voyages, we'll first segment them and investigate them one by one and try to build our first prediction model to do the initial set of prediction. So this might not be the most efficient model, but this is our first step in that particular process. So we'll take one such voyage and try to forecast the fuel consumption based on a set of features. I'll give more details on it as we actually do those stuffs in this particular video. But this is going to be the agenda. So we are going to prepare the dataset for an LSTM based time series forecasting. I'll say what was the reason behind those choices of models as we progress. Let's get started with the video. As you can see my screen, so this is the progress we had so far. So we kind of visualized the different voyages within the maritime dataset we had. So these green chunks represent each voyage and the white gaps represents the gap. So we computed the implied speed, that is the total distance covered by the ship divided by the total time elapsed between two consecutive rows, and computed the implied speed. So we had a threshold like 0.5 nautical miles per hour as a threshold. So whatever the rows that comes under that particular range, and if it is prolonged for 6 hours or more than that, we considered those states as idle states of the ship. So we kind of concluded that at that particular time the ship has not moved. So anything between those things were considered as a voyage. So that was the idea that we did. So to come up with this particular visualization. So after that, what I did was first I filtered the data where we kind of had prolonged idle flag. So not prolonged idle flag, wherever we found that the ship to be idle. So anywhere where the implied speed is less than 0.5 for a prolonged period of 6 hours or more. So I first filtered those data rows, and then I plotted the some of the engine related features like speed through water, and then the torque and the shaft speed. So I plotted these things, kind of plotted a distribution plot, and checked what was the values of them during this idle period, because these were the values we didn't take to come up with that idle flag. We used implied speed. Implied speed is different from the speed through water. So this is the recorded speed of that particular ship during that particular time, but implied speed is the one that we calculated using the distance and time. So they should be somehow correlated in that particular region. We need to check whether the ship was actually idle at those period. So that was the reason behind it. So I plotted it for the speed through water, STW, and the shaft speed and the torque. If you look at the speed through water, it is more around 0. So it is okay, it is actually stating that the ship is in the idle state. Same goes for shaft speed and torque as well. But in case of shaft speed and torque, there are small bump at a very at a period where it is not close to 0. This might be due to, because in some cases due to the water's current, the ship's engine might have produced some kind of power, or it would have tried to move, but the ship might not have actually moved from that particular area. So those kind of values can be okay, because it is not actually recording the actual motion of the ship. So it is only recording the motion of the engine or anything. I'm not very expert in how the ships work, but in a very abstract way, that is okay for now, because that is not actually contributing to the motion of the ship. So somehow our assumptions are good, so it is good to go with this particular kind of split for the voyages. So this is kind of validation step before we go in and dig more deep into it. So, and then I bucketed those voyages as we usually used to do for consecutive ones or zero in case of a binary value, because these are the flag represents whether the ship is in an idle state or not idle state. So I'm not going more details into it because these are kind of repeating. If you had followed the videos from the start, you could have relate to these things. And then I computed the duration of these voyages and tried to again plot a distribution plot around it to somehow have a look at what is the actual duration of the voyages. And yeah, so I plotted them in terms of days first, so duration in days. So I found that it is more populated around zero, and then I actually try to fetch what was the minimum duration. It was one hour, less than a day. It was 1 hour. So what I did was first I plotted it for in terms of days, and I thought it was very it had a range of durations. It had around 0 to 5 days was one set of category of voyage, and then we can call it as very small trips. And then there was a medium size trips which ranged from 10 days to 20 days, and then there were long trips which ranged more than 30 days. It went up to 60 or 70 days in some cases. So this was the observation I got while plotting this particular density plot for the duration in days. So since I had a lot of values around 0 to 1, I plotted again I plotted another density plot which had the duration in hours. So which actually states there was a majority of the trips which were less than 2 hours or so. I kind of filtered out those data because it is not actually needed, because in our the business problem is to actually forecast the fuel consumption for a range of future values. Say for example, if the ship has started a voyage to up to 12 hours or 24 hours, after which they wanted to estimate what's going to be the fuel consumption for the rest of the voyage. So we need a broad length of the voyage. So I kind of filtered out those things because many of those were below 2 hours or so. So I filtered out the voyages which is less than 2 days. I had a window 48 hours, so that it will be we'll be having enough data points to do our forecasting. So that was the thing I did. So I filtered it more than 2 days. If I had said 2 hours before, I meant 2 days. I'm really sorry for that. So I filtered out the data as valid voyages, which are the voyages where it was more than 2 days. So, and then I assigned voyage IDs for each one of them. So each voyage had its own ID. So the valid voyages are the voyages which is more than 2 days. So for those voyages, I assigned IDs to each one of them to actually segment those voyages. And then what I did was I took a random sample of voyages, say for example first 5 voyages, and then I plotted how the fuel consumption trend was actually there during from the start to end of the voyage. And as I expected, that trends were not uniform. I kind of observed different trends for different voyages. So that is the reason why we were very keen on separating the voyages, because since it is having an not a uniform trend around all the voyages, it is actually good to segment them. And I'm not very sure how feasible it is to model different models for each voyages. That's not gonna scale, because we have around 70 voyages, I believe. So building 70 models for 70 voyages, it's not a recommended thing, but we need to somehow generalize the model. But splitting the data set into voyages and treating them as different entities is a much needed one. Maybe we can categorize these voyages using some clustering mechanism, or we can actually use duration as a metric to classify them into different voyages. We can consider the voyages which are very short as one, and the medium ones as another class, and the long voyages is another one. So if you look at those things, like it is not statistically valid, but we can find some kind of similar patterns using the duration buckets. So yeah, that could be one way of bucketing it, but the idea to segment the voyages is because like each voyage have different trend patterns, and we need to handle them, we need to differentiate them before we feed it into any model. So that was the reason why we were focused more on segmenting the voyages. So let us come back to the trends. So this was for the first voyage, and this was for the second one, this was for the third one, and this was for the fourth, and this was for the fifth. So in the first voyage I was not able to find any kind of noticeable patterns. Like there are some peak points and there are some drops here and there, noticeable drops, which is difficult for us to model. But yeah, so this is how the first voyage was there. And in case of second voyages, like there was some kind of periodicity, even though it is not quite equally intervalled. Maybe the other factors of the data set, like we had wind speed, we had the engine parameters like the shaft speed, torque, power, and other stuffs. So they might also contribute to these spikes. So if we are building a multivariate time series model, it can actually take these into consideration. But yeah, like we need to look on it more. But now, like when we visualize it, we were able to identify some kind of periodicity in certain voyages. And again, the third one, it's again random, like it's similar, more similar to the first one. And when it comes to fourth one, again we are able to find some kind of periodicity in terms of the spikes. And for the fifth one as well, it's not as quite relevant as first one or fourth one, but it comes somewhere middle to those things. Even like we can split the trends like this. If we use clustering models, those models can understand these patterns and split the data based on these patterns. So yeah, somehow we need to come to that thing and kind of classify the voyages. But for now, we're not going to that details. We're just going to take one of the voyage and build a model for it, and then we will try to scale it up for the to make it generalized solution for each and every data points that we have in our dataset. So yeah, so that's for the visualization part. So now coming to the modeling. So as I mentioned earlier in the video, I believe I've mentioned, if not I'm saying it right now. So I thought of going with an LSTM setup. Obviously, like the kind of predictions I want to do is I'm not going to take any kind of multi variables here. I'm just going to focus more on the available variables. The thing is, like when we go for multivariate approach during the predictions, we need a set of data points to do our predictions. If it is time for the future values, we don't be needing any, like we can actually have the input in our hand because it's going to be time. We know how the frequency is going to be and we can prepare the dataset accordingly for the input. But if we are going for multi-variables where we have the speed through water, wind speed, torque, and other stuffs, so we don't be having any future values to give us an input to the model to do the predictions. Of course, there are some workarounds to do that. So I'm coming to that. So that was the reason why I took up LSTM, because in LSTM there are two ways in which one can do time series forecasting. One is like just using the available variables, like that we have prior in hand for the future values as well, and do the predictions. And the other one is like it's kind of a sequence to sequence output, where like we can train the model to predict a sequence of future values. Say for example, from like for example, if we consider the present value as t, we can actually compute up to t plus 12 or t plus 24, which computes to next 12 hours or 24 hours of time steps. So we can get a sequence of values for the next 12 hours or next 24 hours. based upon the previous values we have. So the data will itself be modeled like, for each time step, the next 12 hours data will be the output. So based on the previous context, it will be predicting those next 12 hours or next 24 hours. So if it is very vague or very in a very I'm saying it in a very abstract way, the thing is like I don't want to go in details to it, because it is of its own a separate thing to do, a separate 1 hour or 1.5 hours of video to do. But in a basic way, we can extend LSTM to multi-step predictions using multiple variables. So that was the reason why I wanted to do with univariate LSTM first. For now, we are not going to consider any kind of other variables. We're just going to focus on time series data, the datetime column. Along with it, there is another feature, I'll come to that later, but those features as well we'll be having prior in hand before doing our predictions. So that was the idea. So that was the reason why I took LSTM. Also, we can do ARIMA or ARIMAX if we are just doing it univariate using time. But since I have the opportunity of extending LSTM to sequence, where I can do multiple time steps using multivariate inputs, so that was the reason why I took LSTM here. So let's see how we have already, how we have prepared the data for LSTM. In this video, I'm not going to do the LSTM modeling. I'm just going to prepare data for my LSTM system. So yeah, let's go. So as I mentioned, along with the datetime column, I'm also taking another feature as well. So that feature is nothing but the spikes. So since all these trends have spikes at certain points, it have high spikes and low spikes, I kind of engineered a column which will actually check for immediate spike. So I have a threshold value of 500. So here, if you can see, it's around somewhere around 1400 or 1300, and we suddenly get a spike around 2000. So I had a threshold of 500 units. So anything that's going more than 500 in the positive direction or negative direction are considered as spikes. So those are another values that I engineered here as well, because it is dependent on the previous value. So these values can be provided in the input as well when we are doing the predictions or forecasting. So it is not a thing that is dependent like the other multivariate features like speed through water or wind speed. Since this is a feature which is dependent on the past values, we have the liberty to use it here. So yeah, that was the one another feature that I wanted to tell you about. So first, what I did is I first removed some kind of features that I engineered to segment the voyages. So those are not needed anymore. Those were just for the preparing the dataset to compute to segment the voyages. So again, then what I did was, for as I mentioned, I'm gonna take one particular voyage and do the prediction for that particular voyage, and I'm gonna scale it up for the entire dataset. So for that, what I did was I took the voyage which has the maximum duration. So since we can have a large number of data in such case, so I had around 1000 rows of data, which is more than enough in case of an LSTM time series forecasting model, I believe so. I'm not very sure how the prediction is going to be because I've not modeled it yet. I'm just going to experiment it out and check whether it is doing a good job or not. So, and then I filtered that data first for the voyage which had the largest duration. So I have this particular data set which contains longest voyage. So this is the only data set that I'm going to use further in this particular notebook to do the modeling to do the time series forecasting. So I first plotted the trend. So it's kind of not so good because we have some kind of trend for some set of values, and then again there is another set of trend. Maybe it is a voyage breakage. I'm not very sure because we made some assumptions to segment our voyages, but I'm not very sure. And then there is also another outlier value, maybe some kind of sensor error here. So I removed those values before we modeled it. So first, like yeah, the fuel consumption value was a negative value at this particular point. So I like kind of removed it because fuel consumption can't be negative. So I just filtered those data sets, and then as I mentioned earlier, I computed the high spike and low spike. So anything which is more than 500 in the positive direction is no consecutive difference between the consecutive values is more than 500 is considered as high spike, and which is less than minus 500 is considered as a low spike. And then I just checked was there any data that's been missing within the voyages. So this is the same setup that we did for the entire data set. So we would be creating a data frame with start time and end time with the in the frequency of hour countering, like in every hour between those particular time frames, and we'll be merging it with the initial data set that we have, that is nothing but the longest voyage data frame. And then we'll check for any kind of row mismatch. So here the missing hours is 0, so we can continue to do whatever we wanted to do, because like if not so we need to impute those values. So for now it is good, we can go ahead. And then I created a function to basically do the normalization of our fuel consumption. So I did the normalization, and then once that is done, I went for dataset preparation. So this is the most essential part in case of an LSTM system, because LSTM works on previous context. So whatever the things that we are going to predict, it is the model is going to understand the recent past values, and then going to do a predictions based on it. So for example, say the present time is t, then this tth value will be dependent on the previous values like t minus 1, t minus 2, t minus 3, and so on. So what I did was I took a sequence length of 6. So for the recent past 6 values, say for example if you're focusing on the 6th row, so that row will be dependent on the other preceding 5 values. So the dataset will be the preceding 5 values and the current value. So the current value will be the output, and the preceding 5 values would be given to the model as an input. So here, apart from the actual fuel consumption, we have the spike flags as well. It is not actually needed to have lagged values of them as well, but I'm just experimenting it. I'm not very sure whether it will give a good response or not. If it is not giving, I'll just remove it. But for now, I am getting the lagged values of those spike flags as well. So my idea behind is it, like, if the model finds that it had a spike just before or 3 steps before, and if it had understood a pattern, like if it had a spike, it won't be lasting long for 2 to 3 time frames, then it will drop it down. So we need to tell the model those information. So I thought this would give those information, but I'm not very sure how this is gonna work. We need to check based upon the kind of outputs that we get. So I created a LSTM sequence using these kind of information. So ideally for an LSTM, the input should be of this shape. So it should be batch size, comma, time steps, comma, features. Here the time steps is 6 because we are taking last 6 values for each output, and then the features is going to be the fuel consumption, the high spike and low spike. So it's going to be 3, and batch size will be the amount of time steps we have. So that's going to be the batch size. So batch size, comma 6, comma 3 should be the final shape of our input sequence, and the output sequence will be batch size of batch size. So that's the overall idea. So that's what I'm actually doing it. I'm just taking the data frame and slicing it based upon the current sequence, because the data frame, I'm just filtering it out. I'm just having the daytime fuel consumption high spikes and low spikes, and the daytime is set as an index. So these 3 columns will only be there in my data set. So I'm just slicing it and converting it into a numpy array, and then I'm converting that into a PyTorch tensor, and then I'm accumulating all of them, and then this will be done for each time step. Basically this loop will run for the amount of batch size. So for each batch I'll be getting the uh, time step comma features, which is 6 comma 3 tensor. So I'm stacking them one by one as I get it. So finally I'm stacking them all on top of each other, so I'll be getting this particular shape for my tensor. And similarly for output, as I mentioned earlier, it is going to be the values which comes after the sequence length. So because for the first for first 6 values we won't be having any kind of um, outputs, because that will be going as a context. So only from the 6th row we'll be constructing our data frame, as well as for the last six rows we won't be having any kind of inputs, that will go as the final output. So it will make sense when I say show you the shapes and other stuffs. So yeah, so this is what we are having. So this function will basically give us the x and y values. So I'll just print a sample x and y. So this is what we get. So to compare it with the actual data frame, let me just put it here. Yeah. So yeah, so this is nothing but the first 5 values: 0.44, 0.44, 0.65, 0.607, 0.05, 0.06, or until this particular point. So this will be served as an input, and this particular value 0.53 will be our output. Similarly, the lagged values of high spike and low spike will also be recorded here. So those were the 3 columns, and this is the output. So this is how we have prepared our input and output tensors here. And then I created a PyTorch dataset. So this is the procedure when we are modeling with PyTorch. So we need to define this class where we'll be defining the init function, length function, get item function to actually kind of load the data in the data loaders. So this is kind of convention. So in any PyTorch model that we'll be working on, you need to model them like this. So we need to kind of create a class for the dataset class from the PyTorch utils data library, and kind of do this kind of dataset, LSTM dataset. And then we are doing train test splitting to evaluate our results. So I'm just taking a test size of 20%. So since it is a time series data, we can't get a randomized split, so it should be based on the time duration, because we can have a past set of values and then we need to have a future set of values, so it should be continuous. So that was the reason why we didn't do any kind of randomized splitting using train test split from sklearn or any such libraries. So we are coming at a point, we are finding a split index based on the kind of proportion we need, and then splitting the dataset accordingly. And then finally we are arriving at x1 and x test, y1 and y test, and these are the shapes of them. We kind of have 865 rows of data for the train data and 217 rows for the test data. And then we are loading the dataset using the class that we have created. So we kind of wrapping it up with the class that we have defined for the train data and test data, and we are loading it using the data loader. So depending upon the batch size we provide, we'll be getting that much amount of that much rows of the data based upon the batch size that we are providing here. And shuffle, it can be true or it can be false, because if it is kept as true, we'll be getting random values, but for now I'm keeping it as false for actually check how the data loader is loading. So after creating the loaders, I kind of created a loop. I just printed the first set of batch and checked whether they were actually right. So I printed for first 3 batches and evaluated with the actual data frame that I had. So since the batch size was 1, so it should correspond to the first set of rows in my actual data frame. And yeah, that was the thing I did for now. and I validated it and it was all fine. So we have the dataset ready for our LSTM model. Maybe like tomorrow or day after tomorrow we can actually model it and check how our model is actually going to perform. Of course, as I mentioned earlier, this might not be the most ideal solution, because I know that because the output is dependent on multivariables which are in the features, but I'm just taking the time series and I'm just going to focus on the auto regressive part. So we might not get the most optimal result, but at least as a baseline model we might be getting a model which would actually at least find the trends within the understand the trends between the voyages in terms of no, not between the voyages, within the voyages in terms of the fuel consumption. So that is our basic idea, and let's check how this things actually unfolds in the upcoming videos. That's it for today. Thank you.